So thank you everyone for joining us this evening. Obviously a massive thank you to Richard and Sadiq for being with us, and for Bruno for co-hosting tonight. So yeah, a few words, bit of background on the event. And for those of you that don't know me or my business, my name is Barry Cranford. I'm the founder of the London Java community, and I also run RecWorks, which is a tech recruitment company. So here at RecWorks, we try to find ways that recruitment can be a force for good in the tech industry, beyond just getting people jobs. And what that means is we like to offer a lot of things around career development. So things like running user groups and communities, making lots of mentor introductions and workshops and that kind of thing. And we want to do as much of it as we can for free. So we basically make placements and charge companies to find developers, and then take a chunk of that revenue and drive that back into our community initiatives. So it all came about back in 2006, 2007, when I found myself making lots of calls to Java developers, all in the same place, mainly cold calls and mainly getting hung up on people that weren't looking for work, and just thinking there must be a better way to use my time. So we started asking people what they wanted and seeing if we could help in any other ways. And slowly that idea grew into what is now the LJC. And here we are 8,000 members later and 500 or 600 events and running things like this. So yeah, I'm just going to give a very quick shout out for something we're running tomorrow, which is our Lightning Talks events. So for those of you that haven't come along to them yet, please do. It's all about encouraging new aspiring speakers to get involved and giving them a platform to practice. So if you want to come along and support, then please do. Anyway, I'm going to hand over now to Richard Warburton and Sadiq Jaffer, the co-founders of Opsion, for tonight's presentation. So good luck, guys.
Thanks, Barry.
Thank you. All right, hi. So as Barry said, I'm Sadiq, and Richard's
I'm Richard.
as well. just to make sure you got our names there. We're from Opsion, it's a performance tooling and consultancy company. And usually, I mean, this is a conference talk, so usually I'd make some joke here about the irony of it being a virtual conference is that there's no actual free lunch. It doesn't work so well for dinner, but anyway. This talk is going to be about memory allocation in the JVM, how it works, why it's not free, and why it's hard to reason about, and then what tools you can use to kind of better understand it. So,
but first, let's look at what we think is the #1 way engineers can improve their performance optimization skills. Now, it's remarkably simple, and yet it's something that we see so few of our fellow engineers do, and it really hinders people's ability to better optimize their system. And that is to measure before jumping into reading the code. It's good to read your code to understand it, but what we want to do here is take a more scientific approach. We want it to be grounded in measurement and testing rather than just reading the code and theorizing about the way it works. So this talk is going to be all about measuring and understanding and why it's difficult to understand what's going on if you don't do that. We're going to cover a few different topics. So firstly, we're going to talk about what allocation actually means on the JVM, right? It's not C, we don't use malloc. What is the allocation actually doing here? Then we're going to look at how that works under the hood, why it's not actually free in terms of its computational cost, even though it might be really fast and really well optimized on modern JVMs. Then we're going to look about why it's hard to reason about allocation on the JVM, and then look at some tooling to understand exactly what goes on in terms of allocation. So begin with, let's define what allocation actually is. What do we actually mean by memory allocation? Well, this slide on screen has a method, and we've got two local variables within it. We've got a primitive variable, A, that we've assigned 42 to, and we've got an object called B. Now, A doesn't allocate here, at least by our definition here, and B is an allocating local variable. So what's the difference between them? Well, A is a primitive type, an int, and whenever you've got a value in the Java language, you need to have some space in memory for that value to be stored. And allocation is the process of finding that bit of space and reserving it for your value to be stored in. Now, primitive values live on the stack, and there's no real allocation there. They just sit in a slot on the stack on the frame of the foo method. B itself has a pointer on the stack, but it's a pointer to a heap allocated object. So the object is living on the heap. Now, the thing that causes the allocation here is the new keyword, new my object. But it's not just as simple as looking for the new keywords in your code. Things like auto boxing can cause allocation. Things like string concatenation as well. We'll look at a few more examples later. Things get a little bit more complicated, but that's the basic idea. You're reserving some space in memory for a value to be stored.
Great. So Richard has defined what allocation is, and now we're going to look at how does it actually work in the JVM. So the JVM primarily uses what's called a technique called pointer bumping, right? So this is where we have a fixed allocation region, and then we have a pointer to our position in it. And then when we want to do an allocation, what we do is we increment the pointer by the size of the object we want to reserve memory for, right? Well, the size of the object being the size of the header, and then the size of any of the fields that go into that object, and maybe some padding there as well. So we increment our pointer by that size. That's how we do an allocation. Now, it's worth pointing out that that is the path used for nearly all allocations that an application would do, but there is actually a slower path for objects deemed large by the GC, and that goes by a kind of a potentially slower path, right? Because large allocations tend to be far less frequent, and they tend to need to be handled in a slightly different way. So to recap, we have a pointer into our allocation region. We advance that pointer on by the size of the object that we want to actually allocate. But what happens when we get to the end of our region? So we're merrily bumping our allocation pointer along, reserving memory for all the objects we're allocating, and suddenly we find we're off the end of the allocation region. Now that's where the GC comes into play. So at this point, what we can do is we can call into the garbage collector, and the garbage collector might decide to might decide that it's got enough empty space and it's going to hand us a new allocation region that we can pointer allocate into. Or it might determine that actually it's decided that it's not got enough free space, or that it's soon going to run out of space. And in fact, what it needs to do is kick off a collection of some kind to free up space, right? And so it would start a collection. Now, the actual collection and the manner in which it happens depends a lot on the garbage collection algorithm that you're using. So if it's, for example, like a parallel collector like CMS, if it's the parallel collector or it's CMS or G1, then that might be a stop the world minor collection. But it could also kick off a full collection depending on how much of the heap is currently being used. For concurrent collectors like ZGC and Shenandoah, this might trigger a new concurrent collection cycle starting. So we've looked at how pointer bumping works, but how does it actually work in code? So what we've done here is we've taken the assembly code that's generated by the parallel collector in Java 8. And then what we've done is we've simplified a little bit by stripping out some of the bits that aren't relevant. There's things in there like prefetching and such like, but they don't really change the behavior of the allocation code itself. They're merely there for performance reasons. So if we look at this simplified assembly code, what we can see is that first thing we do is we move the current allocation pointer into a register. And on some architectures where registers are plentiful, the actual allocation pointer might actually be cached in one. Then we add the object size, and then we compare to the end of our allocation region, right? If we're over the end of our region, then we call into the GC, and it might get us a new region, or it might start a collection. If not, then we're free to basically update the allocation pointer and to the new location, and then begin populating that object, right? So if you look at the actual number of instructions we execute on the happy path, it's very few. Pointer bumping allocation can be very fast. Now, the scheme we've detailed works fine if you've got a single thread, right? But how do we make pointer bumping work when we've got multiple threads running on multiple cores? If they all share one allocation region, so one allocation region is shared between all threads, then each of those threads will be competing to try and bump that pointer. And it turns out that shared writes, so writes to shared memory locations, scale really poorly on multi-core systems. So to avoid that performance bottleneck, the JVM deals with this by using something called thread local allocation buffers, or TLABs. Now, TLABs are not some special part of memory. They are part of the Java heap. They are just address ranges within the minor heap, but they're exclusive to a single thread for the purposes of allocation. Right? If the JVM didn't have separate TLABs, then obviously there would be they'd all be competing over bumping these pointers, and we get horrendous performance. So each thread has its own TLAB, and that means that any given time there can be many threads in the system, each allocating independently into their own TLAB. So they each have their own allocation pointers into their own TLABs. And only when they come to the end of a TLAB do they need to then request from the GC a new allocation region.
Okay, so Sadiq talked about these great JVM implementation details that mean that allocating objects is really super fast and super efficient. And sometimes I think people hear these details and they think, well, that means allocation is basically free, right? I can just allocate as many objects as I want, and there are no penalties and no costs and no problems. And I think it's worth stepping back a second and understanding why that's not really the case. So firstly, let's take a think about the memory hierarchy within our system. Now, the memory hierarchy is the idea that you've got several different layers of memory within your system. You've got main memory, and then 3 layers of cache on most modern CPUs. The size and speed of those cache differs from processor architecture to processor architecture. The numbers on the slide here are from an AMD Zen 2 chip. But they are kind of reflective of the overall ratios that you might see on a lot of modern hardware. At the top, we've got our L1 cache, which is very, very small, 64 kilobytes, and also very, very fast. If you want to get data into a register on a CPU, then, that's a couple of nanoseconds, and the bandwidth is huge, 200 gigabytes per second. Down at main memory, on the other hand, we have 100 nanoseconds or more of access time to get data into the register from main memory, and a much, much lower bandwidth, though obviously the type of memory here does impact these numbers. Now, what we see often is something that's known as cache washing or cache pollution. Now, if you hear the term money washing, cash washing, you'll hear this expression, you'll think of money laundering, the mafia, crime, Tony Soprano, all things like that. But this kind of cash washing isn't a crime as such. It's not something that's going to put you in jail, but it can still have negative effects on the performance of your application. Cache pollution is the idea that caches are most effective when you have a high hit rate. That's to say, when the data that your CPU needs is in the higher levels of the cache. The hit rate is the ratio of accesses of values that are served within the cache layer. So the higher the hit rate, the more effective your cache is. The problem is lots of object allocation tends to push data into those caches, because as you write data out, it goes out into those caches. Now, modern x86 chips use write back rather than write through caches, and that minimizes the effect of this in terms of the memory bandwidth usage. But you're still spending cycles and you're still pushing older data out of that cache. Now, if you're writing and then reading the same data back in again in the next operation, then that's not a big problem, right? What you've written is live data, and it's that live data which is making the cache efficient. But the problem is, if you're just allocating, then you tend to push a lot of old data out that you may use relatively soon after in order to read some values back in. And when the efficiency of this system is reduced, your CPU sits there and it waits for data to come in from the main memory or the layer of the cache where that data is, and it stalls. Now, a CPU stall is a time when you're not actually able to execute instructions on chip. CPU stalls can often be hard for users to spot because they're not something that turns up in top or VM stat or things like that. They are they look like a certain process is running on CPU, and they look like the CPU is busy. And it kind of is busy, but it's busy waiting for data rather than busy doing something useful. The other thing to bear in mind here is that cache pollution also comes from garbage collectors. Okay, so the garbage collector itself, when it runs, needs to go and read values in your memory. It tries to walk a significant part of the object graph of your Java program in order to find out what objects are live and what aren't. And that has a pollution effect in and of itself that reads certain data values and pulls them to cache that wouldn't be there otherwise if it was just your application running. There's also the more regular cost of allocation, both in terms of the CPU usage of running a garbage collector and also the stop the world pauses that Java garbage collectors are notorious for causing. Now, it's not necessarily the case that you will just pause more when you allocate more. The interaction with garbage collector pause times is more complicated than that. But increased allocation often does mean increased levels of minor collections. So those are young generation collections, Eden collections, whatever you want to call them, in order to free up space for those objects to live within. Now, minor collections might be quite efficient. Java has a variety of concurrent collectors. So things like Azul Zing, ZGC, Shenandoah, these are garbage collectors that... I shouldn't say garbage collectors. C4 in Zing is the name of the garbage collector. But these are garbage collectors that work concurrently. So they don't pause the application in a way that scales with the amount of memory in the heap in order to run their work. But many people are using G1 or using parallel collector, and those things do pause when they do a minor collection. Even concurrent garbage collectors still take up more CPU cycles when they're having to do more and more minor collections. So there's a lot of things to think about there. There's a cost associated with the GC work from higher allocation rates, the pressure you're putting on the GC subsystem. Then there's the time to safe point that comes out of that. So when we run a garbage collection pause, that's a VM operation, okay? VM operations need the application threads to come to a halt in order to run that garbage collector code instead of the threads running. So that process of bringing the threads to a halt is called a safe point. You can see safe point statistics printed out by the JVM if you just use that print safe point statistics option that we have on the slide. TTSP, as it's kind of abbreviated to, can have situations where certain threads keep on running because bringing a thread to a safe point entails polling a certain bit of memory repeatedly. It doesn't necessarily bring threads to a halt instantly, and some of those threads can sit there doing nothing whilst they're waiting for the safe point to complete. That's a waste of CPU. It's a throughput cost. It's a cost on your system. And we talk about TTSP as being an allocation related cost because, again, allocating more causes more GCs, causes more safe points. That's the way these things work. Then there's the cost of the plain allocation in terms of the CPU usage. Obviously, just actually running the garbage collector does take up time in and of itself. And it takes up time both for the stop the world phase, but also for concurrent phases of garbage collector. That's what the little green boxes we have on the bottom of this graph are for, to represent the idea that we have background work being done. It's not just the cost of time that your application's paused. There's a throughput overhead for concurrent work that the GC does, like marking whether objects are live. That's often an operation that can be done concurrently in garbage collectors. And it's also the case that certain garbage collectors, even though they're described as concurrent, effectively degenerate to a pausing full GC state. So Shenandoah has a situation where if you allocate fast enough, it will do a pausing full GC. ZGC tries to avoid looking like it's doing a full GC when it hits this kind of state, but in practice it just has, every time you run a bit of allocation code and call a new, it does a bit of GC work in the thread. It's not part of a global stop the world pause as such, But in practice, it is pausing your application and stopping it from running on different threads. So is it really any better in that kind of degenerated state? Who knows?
Right, so we've looked at what allocation is, how it works. Rich has gone over some of the costs involved and why it's cheap, but it's not free. And now we're going to look at why it's quite hard to reason about just through code inspection, why you really need to measure to understand what's going on. So we're going to look at two cases. We're going to look at expected allocation and unexpected allocation. Now, expected allocation are places where we'd expect allocation to happen, but none happens. And unexpected allocation is places where we have a new keyword. Unexpected allocation are places where we don't expect it to happen because there's no new keyword, and yet it still happens. Both can make it hard to reason about allocation of code just by looking at it. So the first is autoboxing. So autoboxing is where you have a primitive that might otherwise be on the stack, but for some reason we need to treat it as an object. And so we end up putting it automatically into a heap allocated box, hence autoboxing. It's especially important for things like generics, because without it, the usability of generics would be quite poor, especially generic collections. But it's relatively easy to end up with unexpected allocation from autoboxing. This example, we'd actually end up autoboxing each of the ints that we put into the array list. But to make matters slightly more confusing, we'd actually box just less than 900 or so ints per run of this code. It's not 1,000 because minus 128 to 128 are cached to avoid needing to allocate frequently used short constants, right? So if you're doing integer.value off and the numbers between minus 120 and 127, in fact, you get one of the cached integers rather than a new one being allocated. Although this is a good optimization, but at least this hilarious situation where some numerical constant gets changed in code and suddenly you're allocating boxed integers all over your code base where you weren't before, right? If you look at very high performance Java code bases that try to minimize the number of allocations they do, they nearly all use containers specialized to certain data types to avoid this problem in particular. Another source of allocation that often catches people out are operations on strings. So Java's strings are immutable, and so manipulating them often results in allocating new strings. But there's this is a relatively simple example, probably not overly useful example of concatenating string representations of different integers onto the string x. But interestingly, excessive string allocation from concatenation has been a problem from the very beginning with Java. And so the compiler itself tries to do some optimizations to avoid it in simple cases. So in this code, in Java 8 and before, Java 8 and before would turn this code, the body of the loop, into a string builder. And the string builder potentially can save an allocation when x is short because it actually has pre-allocated some, has a char array internally, which is pre-allocated. And if the strings that it are concatenating are short enough, then it doesn't actually need to allocate any more char arrays. Java 9, on the other hand, turns the body of that loop into an invoke dynamic call. And that takes x and the integer I as parameters. Right now, the intention here is that with all the data that needs to be concatenated as parameters for an invoke dynamic call, there can be some smarter optimization done when that code is when that method is called, and we might be able to say size the allocation so that we don't have to actually allocate any more arrays than are necessary, or arrays of dimensions that are not necessary. Java version aside, you could actually replace the this for loops concatenation with a string builder on the outside and merely two appends on the inside. And the result would actually be log 2 fewer allocations because so we're doing n allocations at the moment, and we do log 2 because of the way string builder's internal buffering resizes to it doubles each time, essentially. So the next is immutable APIs and factory methods, right? Now, again, this is not an argument against immutable APIs. Immutability comes with it some advantages for reasoning about code, especially in the face of concurrency and parallelism. So it's not an argument against immutability, but these advantages come with a cost. And that cost is that they can actually do a fair bit of allocation. Richard here has had a bit of a traumatic experience with this local date time, haven't you, or local date?
Yeah, I mean, the Java 8 date and time API is fantastic, much improved over previous versions. But if you just look at the way, for example, this LocalDate.now method works under the hood, it goes in and creates a system default zone. The zone, creates a clock for the system default zone. That involves creating a zone ID. Creating a zone ID involves creating a time zone. Then that creates the clock object. Then that passes the clock object to another method. Then it pulls the instant out of that clock object to get the current time. And then it does some calculations to get the local date out of that instant in time. Now, that is a shockingly complicated series of operations when you might just think under the hood it's kind of calling new and maybe doing a bit of maths. This is often the case with libraries. They can often do a lot of operations under the hood, especially libraries that make heavy use of immutable values. And factory methods are another way that objects can get allocated, not just news. So you will find it very difficult to reason about how much allocation goes on in different systems just from looking at a bit of code like localdate.now. Yes,
indeed. And that takes us on to the next section. So, sorry, I lost my mouse. That's unexpected allocation. So we've looked at a couple of the causes for unexpected allocation, but primarily most unexpected allocation actually comes from the libraries that you use or the deeper parts of your application that are not immediately visible from the actual code that you've written, right? And while I've got a colleague here with head in his hands, that's not necessarily due to any kind of incompetence on their part. That can just be down to the actual complexity of reasoning about large code bases. So we've looked at where unexpected allocation can happen, and we're going to look at some examples, real examples later on. But let's also look at where we have expected allocation, but it doesn't happen. So we're going to look at, this is a class here. It's a vector class. It's a very simple class. It's got two fields, x and y, and it's got this distance method, which when you give it another vector, calculates the distance to that vector and returns that as a double, right? So we've got code here, vector A, vector B. We allocate these two vectors, then we calculate the distance between them, right? Now, what we're going to see happen here is we're going to see how the JVM uses two optimizations and one analysis to make these two vector allocations disappear, like a magic trick. So the first optimization is inlining. Now, inlining is where you basically take the contents of a called method and you take the contents of that method and you actually paste it into the place where it's being called. Now, the advantage of that is normally that it removes the overhead of doing the method call, but also it can open up other opportunities for optimization, and that's what happens here. So the distance method gets inlined, and so it's no longer a method call, and that's when something called escape analysis kicks in, and that's an analysis that the JVM does, where it works out whether a particular allocation will escape from the method it's allocated in. Now, escape means if it's assigned to some other object that itself escapes or is already accessible outside of the method. But it can also be that it's used to a parameter to a method, or it's given to another thread, so it kind of can escape from that method. Escape generally means if something outside of that method could have a reference to it or could actually access it. If it doesn't escape, then what it allows us to do is actually change the behavior of that allocation because we're sure that nobody else other than the current method could actually observe that. Now, because we have inline distance, the escape analysis can be sure that A and B that we've allocated here don't actually escape, and that's when the third optimization, scalar replacement, kicks in. A scalar replacement is where we take an allocation, so we've got an object, and we break it apart into its fields, into its scalars, right? And these scalars are then turned into local variables, if you like. Now, it's worth pointing out here that this is often confused for stack allocation. And while it results in the fields becoming local variables and ending up on the stack, at no point is the actual whole object with header and everything on the stack. It essentially breaks apart an object into individual fields and turns those fields into effectively local variables. And that means that they end up on the stack, right? Now, and that's what happens here. So this code on the left essentially becomes the code on the right. So where we have two new keywords, and we would have expected two allocations, we have in fact got no allocations at all, and no method call either.
Cool. So we've said that it is essentially impossible to reason about object allocation. The JIT compilers against you, libraries are against you, complexity of the runtime is against you, changes in different versions are against you. You might think, oh, well, I just need to give up at this point and go home and worry about something else with my life. But don't worry. It's okay. You can understand what's going on. You just need to use the right tooling to understand what the system is doing at runtime. Now, there's a variety of different tools that you can use for understanding what is going on in your system. One of the most useful when it comes to memory-related problems is allocation profiling. So allocation profilers are things that produce reports telling you what the main allocators were within your system. So they're saying which types were the types that were most commonly allocated, potentially how many allocations happened or what proportion of allocations happened for each type, and also what are the most common stack traces that are related to allocations. So if a certain type was allocated a lot, like a char array or an int array, where in your code was allocating those arrays? What can you use to go back into your code base and understand where that came from? And it may not even be your code base. As I say, it might be a library method that's then being called by something in your code. So the full stack trace there is very useful. So not only allocation profiles are very useful in terms of their output, but there's also worth thinking for a second how allocation profilers are implemented. How do they work under the hood? Because some allocation profilers are better and some allocation profilers are worse, both in terms of the accuracy of the data they provide, because these profiles aren't necessarily all correct or all equal in terms of the data, and also not the same in terms of the overhead on the system that's being profiled. The simplest, most naive type of allocation profiling is called instrumentation-based allocation profiling, or instrumenting allocation profiling. This works by taking allocation sites, so things like that new or the string concatenation, and adding a little bit of bytecode into those allocation sites, taking the size of an object and putting it into some common data structure that adds up these values. Now, instrumentation-based allocation profiling has two big problems. Firstly, very, very high overhead when allocating frequently. And A, you're often allocating quite frequently on the JVM. To be honest, it's a very allocation-heavy platform. B, the key problems in terms of where you're looking for that memory profiling overhead, those are when you're allocating frequently. So the overhead is worst when things are most interesting for you as an optimizer. The other problem with allocation-based profiles is it can defeat JVM optimizations. So the way certain allocation profilers are naively implemented is they take a reference to the object that's been allocated and hand it into some common library code within their profiling agent. And the problem is that this means a reference to the object that you've just allocated escapes into the internals of that profiler. And that means that if it never escaped otherwise, and your escape analysis would mark it as being scalar replaceable, then you've disabled that optimization by running your profiler. So disabling the optimization, I mean, your object wouldn't normally cause an allocation, but simply by running the profiling tool designed to tell you whether allocated or not, cause that allocation to happen, which is pretty bad. Even if you avoid this problem, adding more bytecode to allocation sizes can increase the size of methods. And inlining-based JVM optimizations have heuristics that are dependent upon the size of the method in order to know whether to inline or not. So adding too much bytecode for your allocation measurement, that can cause certain methods not to be inlined and defeat other JVM optimizations. Sampling allocation profiling is a different kind of approach. So that is triggering a sample of what's being allocated on an event that's proportional to allocation. So we saw earlier that there were those TLAB methods, those TLAB spaces within the heap that Sadiq talked about, and the TLAB refills that happen periodically. So they take the they give you a new TLAB. That's a point where you could sample, and that will be proportional to allocation rate. Same thing with minor collections. You can configure the overhead on sampling profilers, so sample less frequently, or you can also sample other things less frequently, like, for example, the stack trace collection within allocation profiling. It's still worth noting that poorly designed JVM-TI agents can disable JVM optimizations, even if you're using a sampling-based approach for allocation profiling. So, for example, calling a JVM-TI operation to inspect a local variable disables escape analysis, which that's a really bad impact for your operation, for your agent to have. But a well-written sampling allocation profiler can be very, very low overhead. The one we have in the Option continuous profiling tool has less than 1% overhead on systems that we've measured and used it on. And it's something that you can use in production because the overhead is that low. And that's also really nice because it means you don't have to go and produce performance tests or benchmarks in order to understand, in order to run your memory profiler and understand where the memory profiling problems are. You can just look at the real production behavior.
All right, so we're going to look at an example here now, and we're going to go and do some allocation profiling live, and hopefully it's all going to work great. So this is a rather simple example. Here we go. It looks pretty basic. So the core of it is this remove duplicates method, right? And so what that does is it takes the first element from the pass list, removes it, and then it also removes all duplicates off it from the list, right? Simple stuff. Richard, what do you think the allocation behavior of this method is going to be?
Well, I think you're an evil man, Sadiq, and you're trying to trick me and fool me here, aren't you? So we've got a list of boxed integers, and we pull out the first value on that list and try to remove the duplicates for the first value. So that first value is in a primitive int on the stack in the remove duplicates method, but then you compare it using the equals method within that remove if. So I think there's going to be a load of auto boxing as we pass that first into equals, and that's going to cause a load of unexpected allocation. That's my guess anyway. All
right, that's a pretty reasonable guess. So we're gonna go look at what it actually does now. So we've wrapped a program around this method. We create a list with a bunch of increasing integers, and then we call this method and base until the list is empty. So we're going to use. I'm going to switch over to a browser here, and we are going to use we're going to use Option's allocation profiler here, right? So as Richard mentioned, this is the Option continuous profiler, supports allocation profiling, and there's CPU profiling and wall clock profiling and others. And these are designed to be run in production systems, and they're commercially tested as well to make sure that they're compatible with all the JVMs that we support. So we're gonna, oh no, I've got some faces in the way here, one sec. So we're gonna run a report now on this example. And we said, what did you say, Richard? Integers?
Yep.
Well, you were wrong. I like saying that to Richard.
There are some integers.
There's some integers here, but actually, now this is being run on Java 14, and the most allocated class for this particular example, or most allocated object in this particular example, are actually long arrays, right? So what's going on here? So let's go and try and understand where. So we can go look at the call site here. And these are all being allocated. So we've got example one main, example one remove duplicates, which is our method, array list remove if, and array list mbit. So let's pop into the IDE for a second. I've got an IDE here. This is the correct one. Yes. Okay. So we've got our remove duplicates method here, right? So now let's say you were just looking at this. You'd seen this in the diff. Load up into your IDE. We click on that, and we go and we look at this method here. So this is collection remove if, and we'd look at it and say, well, yeah, it probably allocates an iterator, but doesn't look like the iterator escapes. So it probably gets doesn't actually get allocated, and so on. But actually, we just saw that long arrays are the dominant thing here. So what's happening? Well, it turns out that this is a default implementation on the collection interface of remove if, but array list has its own specialized implementation, right? And as you can see, array list specialized implementation is a lot more complex. And it's more complex because it supports so-called reentrant, what it calls reentrant access to the list. So that is the lambda that you pass to remove if, the predicate. It can access the list itself. So if, for example, if you wanted to remove an element, if there are at least 50 elements of that type in the array list, a very inefficient way you could do it is to scan the list inside the predicate. And ArrayList supports that. And in order to support that, it needs to track what the indexes are that are actually removed, where the predicates return true. And so actually this ends up involving, well, it needs some space. And so it ends up involving an allocation of a long array, right? And you can see this rather morbidly named death row here, long array. And that's what actually gets allocated each time you call it. So it's worth pointing out here, though, that this behavior only happens in array lists, right? If you passed in a linked list, you would use the remove if implementation on collection, which might involve the allocation of an iterator, may not. Now, what's actually really interesting here, and let's jump back to the slide, is the behavior of this actually changed between Java 8 and Java 14. So the behavior, just the remove if implementation changed between Java 8 and Java 14. In Java 8, a bit set was allocated regardless of whether any locations actually evaluated to true. In Java 14, there's a really cool optimization that avoids doing that. So it actually only starts the array from the first index that actually the predicate returns true. And that means that actually it will not need to allocate an array that's in proportion to the size of the list, but in proportion to the size of the actual number of predicates that are true. So that's changed, but also what's changed here is the actual behavior of autoboxing. In Java 8, you do in fact end up allocating a lot of integers when you run this code. And Java 14, you don't. So there's a significant difference in the allocation behavior of this code between the two JVMs. And it might look like a contrived example here, but this is very similar. This behavior of remove if allocating is very similar to something that we actually hit in a production code base, in a high performance production code base. And this was a source of excess allocations on a critical path. So the next we're going to look at, we're going to very quickly look at how this can work in a larger code base. So we're going to look at a more complicated systems example. And this is, again, the kind of thing you experience when you're doing performance optimization on real systems. You can no longer look at small bits of code. You've got to understand how things fit in the bigger picture. In the UK, property transaction data is available publicly. You can just go and download CSVs that have, you know, all of the transactions for the last year, month, or years. This system is basically an HTTP front end and a cache in front of that data. I set it running a little while back, and it's actually got a constant load being thrown against it of HTTP requests. And we're going to go look at how its GC and memory behavior looks through Option Systems and JVM Diagnostics dashboard. So this is Option Systems and JVM's System and JVM Diagnostic dashboard is a system which essentially pulls information from the GC and the system that the JVM is running on, and then allows you to actually dive in and understand the different parts of its behavior, GC and other parts as well. So we're going to go and have a very quick look at that and see what it is doing. So let's jump over here. So we're going to go and have a look at this dashboard. So this is our application here. Now we'll scroll right down and start with the application pause time. So application pause time is the amount of time that an application actually spends pause relative to doing productive work. So we can see this application sometimes it's spending up to 75% of its time paused, and it's only doing that really for about 2.5 minutes. But during that period of time, it's effectively doing very little work, right? And we can see that it's also doing a lot of collections. So this is the parallel collector. So these are young or collections, and we can see that it's doing a load of collections here, and that's because we are actually doing a lot of allocation at that point in time. So the system is doing relatively a decent amount of allocation at this point in time. And normally, if you encounter this with a real system, what you would see is everything is fine. We've got a constant load going against it, but suddenly the system is slow. And why is it slow, right? And trying to actually track that down from metrics can be quite difficult. And this is where combining a metrics-driven approach that measures what's actually happening with your allocations and profiling becomes very powerful. So we can say, okay, well, let's actually go and have a look here at this particular bit on the graph. And let's go and have a look at the allocation profiling data for just that bit where our allocations were spiking. And what we can see here that actually during that bit where allocations are spiking, 51% are actually char arrays, and the next highest thing is strings. And if we look at the char arrays, we actually realize that they are coming. If we look at the stack trace here, we can see all the common stack traces. So it breaks down the common stack traces that we see these, and these are all coming from CSV reading. And so from this, we can look at this and say, okay, well, let's go and have a look at sales. Let's go and have a look at this particular method here. So we saw that we were in sales data, and actually what we can see is that we've got a rather simple bug here, which again looks contrived, but actually is something that we've seen in real systems, where the issue is very simple, but it goes through many layers of the system. But when you have allocation profiling behavior, you can actually get stack traces and look at the root cause of where things are coming from. We can see that we're supposed to be caching this CSV data. And in fact, our IDE is telling us that we never assigned this static cache that we created for it. And the fix is very simple. We essentially just need to do this, and we would be away. Now, it's worth pointing out that the only reason why we see that behavior, that spiky behavior, is because this system actually invalidates its cache, its whole cache, every few minutes. If, on the other hand, it was expiring individual cache elements based on some timeout, we wouldn't see that spiky behavior. But what we would see is just a high background rate of allocation and CPU usage and high GC pause time. And we would just expect that that's the way the system works. But only by actually looking at the system and by measuring it can we go in and see what it's actually doing and how it's actually maybe not working in the way that we think it is. Just going to switch. Oh no. You can do this. There we go. Richard, you're muted.
So in summary, Sadiq's talked about a few ways in which you can use allocation profiling tools to find problems within Java systems. But the key idea here is to avoid excess allocation. Allocations are really cheap. There's a lot of great work gone into making sure the JVMs are really well engineered and the garbage collection is efficient and all that kind of stuff. But still, excess allocation has a cost. There's no need to go and prematurely optimize things or like tomorrow morning go into work and write your own cool custom object pooling implementation or anything like that. We're not saying to do that, but often when you've got bottlenecks in your system, throwing an allocation profiler into there and seeing whether you can get some easy quick wins and remove the worst of things is a great way to improve the performance of your system. We also talked about how we had different methodologies for approaching performance problems. Listen to Mary Kondo. Mary Kondo says, only reading code does not spark joy. We must have a think about this. We must thank reading code and throw it away. We should think about the memory allocation patterns of our systems, the presence of JIT compiler optimizations, libraries doing things which could be completely nuts under the hood, different cost models for different GCs, things like that. It's always worth taking the right tool to understand these problems. And the right tool in this case is a memory profiler. Memory profiles are a great tool to have in your tool belt, especially memory profiles that can run in production. It's a bit like a measuring tape for object allocation. It is really easy to use, really easy to find low-hanging fruit. There's often great optimization opportunities within your system just waiting for you to find them. And thank you very much for listening to the talk. It's a great opportunity for you guys to put any questions you have into the chat. I've seen that there's a few questions there already. We run a business called Option. We help customers both through consulting and tooling to find and fix their performance problems rapidly. One of our customers called our tooling a magnifying glass for their servers. So they're very, very happy with that. Okay. There's a few, I don't know if you've seen this, Sadiq,
No,
but
I haven't.
there's a few questions in the chat. Shall we pick through these things here? So the first question someone mentioned, swap partitions are not part of the memory hierarchy. Yes, I guess they are kind of at the bottom of the memory hierarchy. But obviously you want to try and avoid things being in swap. They are the cellar of the hierarchy. That's a good way of thinking about it.
Yeah, you're also right there that it is a squared Euclidean distance. I just couldn't fit the whole thing on the slide. But I will definitely put that as a note on there.
Yeah. Isaac Jordan asks, what would be some example tools that use the instrumenting method? And as Raphael points out in the comments, a lot of profilers have instrumentation-based allocation profilers. The specific example that I gave where the instrumentation-based profiler disabled scalar replacement and escape analysis actually came from JVM's allocation profiler, which I discovered when using it at one point in time. There's JProfilers. I don't know whether JProfiler in your kits do. I know they have instrumentation-based systems, but they might have that type of issue as well. Flight Recorder has a good sampling-based profiler, and so does Async Profiler as well as our own tooling. But most allocation profilers are often, aside from those, are often problematic. Another question in the chat was, how would you make a decision to look into allocation profiling versus just focusing on CPU profiling directly? And I think Sadiq in his demo earlier showed some example metrics that were available within our tooling around memory information. And I think that's a good way to drive that kind of decision-making process. Whether you've got a CPU bottleneck that you can just look at CPU related profiling directly. If you've got a memory bottleneck where you want to reduce the amount of memory used by your system, that's something that can be helpful for seeing what's causing allocation, though allocation isn't just isn't exactly the same as the heap consumption of those objects. But there's also the question of what's causing garbage collection rates. And you can see if you've got graphs on allocation rates and GC rates, correlating those things together. The other thing I would say is once you've got a tool in place that lets you look at CPU profiling and allocation profiling, and it's just like clicking a different tab in the UI, it's very easy just to go and have a look at both and just see what's going on there.
Yeah, a lot of the philosophy behind Option has basically been to continuously profile. So our customers essentially run our agents all the time. And once you've got it in place and there's no procedure necessary to actually hook up to a production service and run and gather some data and then go off and look at it. Once you've brought that barrier down and it's just a matter of essentially clicking a button on your web browser, answering some of these questions effectively after every release even is very, very easy. And people actually tend to just do it fairly often.
Yeah. Brian Quinn asks about comments, insights on metaspace memory usage and native memory usage. There are some buffer pooling plugins that you can use in JVM to see different buffer usages with memory usage for native memory usage. In the past, I have inspected problems like this and just done it with kind of custom bytecode instrumentation on creating buffers and things like that. I don't know if you've got any other useful insights there, Sadiq.
Gmalloc is good.
Gmalloc. Oh yeah, that's another thing to think about.
Yes. Metaspace and other native memory usage might be one to discuss afterwards. Yeah. Is it causing you because normally when you have a metaspace collection, it can trigger a full GC, and that tends to be kind of problematic. But that can often come down to sizing. You should really hit that for healthy applications. You should hit that. You will hit that early on, but then you shouldn't hit that at steady state. If you've got something that, if you're hitting that on a regular basis, you may actually have some kind of class loading issue or leak or something like that.
Yeah,
that would definitely.
Yeah, it's worth. I mean, Option as well as a tool will give you data on metaspace memory consumption. It's worth noting, and also, as mentioned in the chat, you can get that information out of garbage collection logs. There's a link there to a custom object pool. That's cool. Relationship between allocations and heap usage. I mean, it's not a direct relationship between allocation rate and heap usage. If you want to understand what objects are using memory in your heap, then obviously heap dumps are one approach, or you can also look at the JMap-histo option to get a histogram of types and heap consumption. But you can't just look at allocation rates and say that's what's using up the most objects in the heap, because it's a churn related metric, whereas heap usage is a kind of a steady state, a point in time related metric. So there's different ways and different tools for finding out information for those different things.
Yeah, I mean, you might be able to get some hints from allocation profiling, but it's worth realizing that, yeah, it's not going to tell you what's necessarily still in memory, because you might just be churning things quite quickly.
Yep, cool. Fernando asks, the tool produces reports. So Opsian produces web-based reports that you can just share or see, the kind of things Sadiq showed in the screen share that you can just share with your team or see there. Jan, any comment on the Azul garbage collector? I remember a talk, possibly in this series, where that was described as almost a magic bullet to resolve prohibitively long stop the world pauses. Azul Zing's C4 collector is very good. It does reduce a lot of stop the world pauses. But it's worth noting that there are now some OpenJDK collectors that have sort of improved the state of the world there. So ZGC and Shenandoah. You can actually head over to our blog on opsin.com/blog and see a few articles we've written on how Shenandoah and ZGC work in a lot of detail, both written by Sadiq, actually, and with kind of feedback and comments from the authors of those collectors. Now, concurrent collectors are good at reducing stop the world pauses, but bear in mind that they won't reduce the other kind of impacts we've talked from high allocation rates in this talk. So it's not like it's a magic bullet to all memory related performance problems. It'll just improve the stop the world pause case. If you've got anything else to add on that, Sadiq?
I was also going to say that nothing in the world is free. I mean, free lunch, as we said in the talk title. Like, you're often trading off latency for throughput in things. I would say, though, that you, like everything, you want to actually have a representative workload, and if you're going to try new GCs, actually test them on a representative workload to make sure that you're not just necessarily optimizing for the shortest possible pause times at the expense of overall throughput of your system, if that's also one of your goals, right? Yeah. So I was just reading another question here as well. Just a thought here: wouldn't profiling on top of a load test defeat the purpose of singling out issues? Often testing with production like workloads and simultaneous profiling ends up a wild goose hunt. Essentially, yes. That's part of the reason why we also built out Opsion for doing production profiling. In previous high performance work that Richard and I have been involved with, it's been very difficult to actually, and in my experiences, it's been very difficult to produce synthetic workloads that actually match the kind of things we're seeing in production, especially when production workloads were changing on a pretty frequent basis. And so actually measuring what production itself was doing became the gold standard. And effectively, if you're trying to optimize production, then you should really measure what production is doing. Because as we've seen from some of the other optimizations that are here, small changes in how code is used, or what the dependencies are, or how things are warmed up, could actually make changes to how your allocation profile behaves. And so, the gold standard is you should do this in production, ideally with production workload. And if you're going to do that, you might as well do it all the time, kind of thing is the position that we come from.
Absolutely. That's why our tooling kind of is a more production-focused system rather than developer-focused system. Great.
So as you say, recording incoming requests and replaying them later, that can work depending on how big your system is. But you have to also be very careful, because there are things, there are issues that come from that are maybe not totally obvious. So one of the bugs that we had to deal with was an issue where we had a misbehaving SDK out in the wild that was sending requests back in parallel, was sending several requests back that were hitting our front-end systems that were then contending over one bit of data. And if we'd simply recorded the traffic from one of those front-end instances, or even all of them, and not replayed them in exactly the same way down to the concurrency involved, we would never have found that issue. And in fact, we only found it by doing some profiling.
Yeah. The other thing about recording the incoming requests and replaying them is it's often quite dependent on you being able to anonymize that data, or make sure that it's safe for you to do that without any personally identifying information. And also that it's not just kind of the incoming requests, but if you've got other services that you're talking to downstream, like a microservices fan out case, then those are things that you need to be able to replay the request responses to those systems and their performance, as well as the incoming data as well. But it is an interesting way of validating those performance problems, at least. Cool. Anything else to add, Sadiq?
No, I think that's it. If anybody's got any other questions, our Twitter things are on the front page, or you can go to the website and you can send us an email. Yeah.
Cool. Thank you very much.
Thank you, guys. Thank you for the great talk. Yeah. Guys, if you have any other question, you can put it in the chat, or you can also unmute yourself and ask them directly. If we are done with the questions, then we let Richard and Sadiq dinner.
Yeah, thanks a lot. Thanks a lot, guys.
Thank you, everybody. Have a good
Thank you very much, guys. It was a really great talk.
Bye.
Bye.